Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Yeah, we are live.
Hello, everybody.
Hello.
Welcome to another episode of Ask Us Anything about electrochemistry. I'm Dr. Alex Paraff, and with me is my colleague, Dr. Neil Spinner. And it is during these live streams that we try to answer any and all questions that you have about electrochemistry, because it's a very complex and complicated subject. And we get a lot of questions from you on YouTube, via webinars, telephone, emails, and we figured this is the platform for trying to answer some of those questions that need a little bit more time, a little bit more technicality. Now, in our time of making these live streams, we have found that questions that are super ultra specific, like, oh, what's the activation energy for a copper electrolysis bond or something like that, probably can't answer because it's a very specific number. And similarly, if you have a question that's super broad, like what is electrochemistry, or what is cyclic voltammetry, or explain EIS, that's also something that we probably can't answer within like a 10 or 15 minute time frame, because we do get a lot of questions and we do want to answer as many of them as we can. So questions that are somewhere in the middle probably work best. And we also have a lot of resources for those bigger, broader questions. We have webinars on our YouTube channel for our Tier 2 members. So if you want a complete EIS tutorial, those do exist for our Tier 2 members. Additionally, if you do have a question, if you're a Tier 1 or Tier 2 YouTube member, you can join us on Restream to talk about it and show us what your data is, and we can get to see your face, and you don't have to just type your questions in if that's something that you want to do. We usually run this live stream for about 2 hours, about give or take however many questions. We're using Restream as the platform for broadcasting it, but you can watch on YouTube. You can also watch on Twitter. There are no stupid questions, but questions that are within that range that I mentioned earlier tend to be the best and most appropriate for this platform. If you have questions, we apologize in advance if we mispronounce your name. But I think those are all the kind of boilerplate things.
Yeah, there's no stupid questions, only stupid hosts.
Only stupid hosts.
That's right. That's what we're here for your made up information. No, I'm just kidding. The only other thing I will say is that that little short intro video, in case it wasn't obvious, we have a podcast coming out in about 1 week, actually, from today. So for those of you who are members of our YouTube channel, it will be available early access on the 7th. That's next Thursday.
That's next Thursday.
Thursday.
You'll get access. to
And
the
then
first 2
for
episodes.
everybody else, for general access on all of the things and the places where podcasts exist, it will be January 4th. So please do give it a listen. It'll be funny,
Yeah.
lighthearted. Alex and I have worked for a little while on these podcast episodes. It's a little bit, electrochemistry, troubleshooting kinds of normal things, but mostly it's us making really bad jokes and movie references.
Yes, that's right.
It's just
That's most of
and
it.
playing games and it's a whole lot of fun, and I hope it'll give you a laugh. While you're in the lab polishing electrodes for the next hour of your life, watching it waste away. Listen to us while you waste your life away.
Yeah,
that's
right.
what I demand. So yeah. So thank you all for joining us on both YouTube and Twitter, if you're on, or X or whatever it's called now. If you're watching us, and to the best of our knowledge, it is not possible to pose a question on Twitter into what we're seeing in our platform here. So Alex, you
I'm
usually
keeping an eye on the chat and
monitors
messages
Twitter
on
if there's
Twitter.
a question on Twitter X. But the most of the questions that we can display, like this first one here from Animesh, who I'll answer in just a moment, it's easier to do so on YouTube. But in any case, if you are joining us on either platform, thank you and welcome, and we look forward to your questions. So with that being said, I do see the first question here from Animesh is about lithium plating. So you asked, you want to know about lithium plating. I said specifically what are you interested in? You want to know if lithium plating occurs in lithium ion batteries over time. So the answer to that question is hopefully no, but unfortunately sometimes it does, right? So I'll get my little drawing PowerPoint, blank canvas up here for you. So share screen. It's like I've never done this before,
It's been a while.
It has. Yeah, actually, happy Thanksgiving for any of those in the US who had the holiday. And Alex and I were just in Boston this week at the Materials Research Society MRS conference.
Yeah,
so
right.
for those of you who may have showed up at our booth or said, came up to us in person, thank you. We appreciate it. And it was nice to see people in their human faces in real life and everything. So yeah. Okay. So to your point, lithium plating, right? So a typical lithium ion battery has an anode and a cathode, right? Now, the best, in theory, way that you would run a lithium-ion battery would be to have lithium on either or both sides. Because fundamentally, a lithium-ion battery works where you have lithium plus ions that go from the anode to the cathode, okay, during discharge. And then the lithium ions load up in the cathode, and then they go back to the anode during charging. And it's just this game of playing ping pong with lithium ions, back and forth, back and forth. That is fundamentally, in the most simplistic way I can possibly describe, before we, without talking about all of the actual real chemistry and details, of course, there's way more complex than that, which you can imagine. Fundamentally, I'm bringing this up for one reason, which is that as lithium ions are passing back and forth, well, they have to go somewhere. Now, typically in the anode, it consists of graphite, right? It's just carbon. And the cathode is some sort of usually metal, I'm just using M and N as like, this could be cobalt, nickel, manganese, whatever, oxide, it's usually some transition metal oxide, right? And so when the lithium is getting charged up into the anode, it's usually displayed as LiC6, something like that. Okay, so fundamentally, the lithium this isn't really plating because this is an elemental lithium. It's getting loaded up into the lattice of graphite, of carbon. Okay, and then when it loads up back into the cathode, it's more like Li. We'll just put Y as the subscript because the stoichiometry will vary depending on how charged it is or discharged it is. But it's getting loaded up in the cathode, not plated as lithium metal. It's getting loaded up into the lattice in some manner of structurally of your cathode material. Okay. Part of the problem with lithium-ion batteries is a thing called dendrites. You may be familiar with dendrites, which may be why you're asking this question. If you're not, basically physically my anode, my cathode, and I have a separator in between, right? This is anode, cathode, and this right here would just be like the separator. Okay. So as I'm passing back and forth, I have electrolyte, some small amount of electrolyte. It's not a lot because this is usually pressed together very tightly. But fundamentally, I have electrolyte in between. And so my lithium ions are going back and forth during charging, discharging, whatever. Well, they have to go through a separator, and the separator is electrically insulating. And so it prevents a short, right? If the anode and the cathode were touching, there would be no battery. There'd be no need. Everything would just immediately discharge and you'd be over. So what happens when and if lithium metal starts to plate on one side is it forms what's called a dendrite. And so microscopically, you can imagine the anode, it's not perfectly planar. It might be some surface like this, but if lithium started plating, you might sort of get this spike. There's no telling which way it would plate, right? Who's to say if it plates, it's going to plate an even surface? No, well, it might grow preferentially out. And so this is called a dendrite. This is what can happen, and it's catastrophic to a battery. So what happens is if that occurs and you have your separator here, well, the separator can get punctured. And then suddenly my anode and my cathode, now they're touching because of this dendrite, right? It grows, it physically grows and extends. It could happen at the cathode too. I'm just drawing it from the anode for picking one of them. But if that happens, then now suddenly I have this is called a short, right? Okay. And so this is one of the things that makes batteries potentially very dangerous, because this can cause a failure. It can cause dramatic increase in heat generation because you have a very rapid passage of current inside the battery immediately, a rapid discharge, changing of the stoichiometry of the microstructure. This can lead to a thermal runaway and a dramatic failure event. Okay. And so if lithium plates like that, now when you're doing testing, I will say, right, often when people are testing a novel material for anode or cathode, you use lithium metal for the other side. And so then obviously it's plating, because if one side is not graphite, it's just lithium, well, then obviously lithium is the thing that's plating on during discharge or charge, right? And it's just not a long-term sustainable solution. Basically the reason we use graphite and then transition metal oxides is because over time, folks in the battery research community realized that using pure lithium metal is not safe. It would be wonderful if it were. And lithium-ion batteries are the state-of-the-art technology for all of our phones and consumer electronics and even EVs at this point, right? And that is almost in spite of the fact that we can't make them as great as they are theoretically, which is to say pure lithium metal is like the highest power density, energy density, efficiency, everything, right? But it's not safe. And so nobody's interested in using a phone that explodes in 2 seconds, right? So, well, maybe some people are. That'd be kind of exciting. But fundamentally, that's kind of the point. And so hopefully the answer to that question, right, but just to sort of summarize and conclude here, I suppose, is that hopefully plating doesn't occur, because if it does, you might be in for a world of hurt. You might have some big problems. Now, over the course of charging and discharging normal, there will always be a little bit of lithium plating that may occur. It's inevitable. Like you're going to get some lithium that'll form here or there, and hopefully it's not enough to form a dendrite. Hopefully it's not enough to disrupt things too badly, and that during the subsequent charge or discharge, it dissociates and then it's no problem, right? But that is one of those major concerns of battery operation. So good question. Good question.
Very good. You are the battery expert, so I default to you.
Expert is such a generous term, but I appreciate it.
Oh, I mean, it's not like you got like your Ph.D. in doing lithium-ion battery research.
For any of you out there who are getting PhDs, it's like, I hope that you experience this someday. You're going to be relatively knowledgeable about whatever you've studied, right? And whatever it is. And then you're going to be thrust into a place where you are the only one who knows anything about that topic. And so by default, you're the expert. Yeah. Like I'm the default expert on batteries because I'm the only one at my company who has that experience. I just happen to be the only one here who really did my PhD studying batteries. So I'm an expert, and I'm really not trying to be falsely humble. I always try to be somewhat cognizant of the fact that like I know some things, but there's so many people who must know way more than me. So it's always sort of fascinating to me to be looked at as an expert in anything. It's the post PhD world is very strange. It's a very strange phenomenon. If you don't want to have a God complex, if you have a God complex, it's great. You know.
Oh no, I have like no God complex from
No,
getting
you
a
certainly
PhD
don't.
at all.
And I hope
Not
I
even
don't. I don't
close.
know. I try not to be. It's one thing to want to be, you want to be confident, right? You want to be confident about what you're competent about. You want to
Well,
be
yes.
you want to be confident that you can help. That's why we're doing this session.
Yeah,
If I didn't think that I could try to help y'all with your electrochemistry stuff, we wouldn't do this live stream,
Oh yeah.
But on the other hand, it's like I really hope that I don't ever get to a point where I just think I'm so much better or smarter than anybody. That's just not, you know what I mean? That doesn't help anybody, and it certainly doesn't help ourselves, right?
Uh,
Now we're getting to philosophy.
yeah. Now we're
here.
getting into philosophy, which I'm not gonna go into it. But I just feel like some of the like what we consider like some of the most successful people on the
Yeah.
planet, they had like a crippling sense of like insecurity, but they also
Yeah.
had like I think some of them also had like a superiority complex as well. So maybe it would help if you thought you were all
Yeah.
that in a bag of potato chips, as the saying goes.
There's a sports ball term, so you'll have to bear with me.
Oh,
There's
yeah,
a sports-
uh-huh.
But it's like on an NBA, on a basketball team, you always have to have one guy who there was a sports writer I used to watch who he called the irrational confidence guy.
Mhm.
So like,
Yeah.
you're down by 2
Yeah.
and you desperately need a shot. And it's like, there's just always one guy. You need to have one guy on the team who, it doesn't matter if he's a 12% 3-point
Yeah.
shooter. He's going to heave that baby up there
Yeah.
because he just is like, I don't care. I'm going to make it,
Yeah.
like
Yeah.
he's irrationally confident.
Yeah.
And that, you sometimes need that.
Sometimes
You
need
need
that. Yeah.
it's not that he, maybe is the best, but he believes he's the best.
Yeah.
It's like the power of belief or something. So
Power.
the irrational confidence. I like it.
Yeah. All right, we've gotten quite a few questions. This is
Mm.
great. Keep them coming in.
Yeah.
And for those of you who are new, welcome. We appreciate all kinds of new folks coming in. We have looks like a 2-part question from Axel Erickson. So he says there are numerous techniques for determining the flat band voltage of a semiconductor electrode, but why is it interesting to know? What can I use it for? He continues to say, how does flat band voltage differ from the open circuit potential if we were to compare them? So I know a little bit about the flat band potential. It seems like a thing that's uniquely situated for semiconductor materials. And I really wish I had a stronger knowledge of this. But basically, this is kind of the way I kind of understand and or see the idea and concept of flat band potentials, which is that whenever you have like some kind of semiconductor material, you have so you're always given this kind of band diagram, and then there is there's like a valence band, and there is a conduction band. I'm just gonna put it up here. Conduction. I wish I could type better or write better. And when we think about a semiconductor material, these are materials that are partially conducting and partially insulating, and they're normally characterized by the fact that when you photo excite them, when you shoot a photon, you get an electron or something from the valence band to move up to the conduction band at a specific wavelength of light. I think most people probably know this. The Fermi level of the semiconductor is defined by the I don't know. There are many definitions. I like the one where it's the energy level where there's a 50% probability that you'll find an electron there, and it kind of is just the halfway point between the conduction and valence band. But if you dope the semiconductor with either N or P type doping, you can move the Fermi level because there's more electrons in one than another, or depleted, you can move the Fermi level up or down such that that probability is, again, 50%. Now, this is all just semiconductor photophysics. At this point, there's absolutely no discussion of electrochemistry, which is when you put this thing into a solution. And so when you put this whole system into a solution, so this thing is dunked in water, you get a lot of the same thing. But from my relatively limited knowledge, the Fermi level is equal to or equivalent to the flatband potential. And Neil, correct me if I'm wrong, because I know you've done some things like Machaki and have worked with people about it.
I mean, you do a better job explaining this kind of fundamental stuff in with respect to like valence bands and the energy levels and everything than I do. Yet I have all I'll say to this, and I'm gonna let you finish. Is that while I know Mott Schottky as an impedance method and its application to obtain an estimate of the flatband potential, I have never, to be perfectly honest, quite been able to conceptualize what flatband potential means and what its significance is. It seems to be elusive to me, and every time I've tried to understand it, I sort of end up with this circular logic, or wherever I'm looking perhaps gives circular logic, where it's like the flatband potential is the potential where the flatband is, and it's like, well, that does not help. What's the flatband? Like, I actually have to be honest, somewhat of a lack of understanding myself precisely what it means. I can conceptualize the electron donor density a lot better than the flatband potential. I'm not 100% sure I have a great conception of it. So I think what you're describing is probably the best way that either of us will be able to describe it.
Okay. All right. I'm just making sure, because
but you're saying it's basically the Fermi level in some representation.
It's equivalent to the Fermi level when you put this thing in solution. And so the other part of Axel's question is related to OCP, like the open circuit potential. And how exactly are these two things related? And I think one thing to note about OCP and kind of like what it is that OCP just by itself, I view the Fermi level and the flatband potential as these, we use them to characterize systems, like, oh, this semiconductor that was n-doped or p-doped has a flatband potential of this. And the flatband potential is a voltage. It's a potential, and it's measured with respect to something. And similarly, OCP is really just looking at what's it's the open circuit potential, but it's the open circuit potential between, say, your semiconductor and your reference electrode, or the rest of your system. Like, that's what OCP is measuring. It's a passive voltage measurement technique of the entire cell. So when I think about open circuit potential, I'm channeling a little bit of my Dan Shearson here, a great professor, a very smart professor at Case Western, where he actually doesn't like OCP just by itself, because OCP really should be a measurement of the thermodynamic differences between these two reference points. But more often than not, these reference points are kind of vague and we don't know what they are. So when you have a solid and stable reference point that's well characterized and stable, and it's like SHE or something like that, then the open circuit potential simply references the difference, like what the flatband potential is with respect to your stable reference point. So that may be another way that you can use to perhaps measure the flatband potential, or at least get a general idea of it. But I know that there are more specific techniques, as Neil said, have to do with Mott Schottky, that give you a little bit more. Let's see, like a lot of people use, and let me just share my screen. I just found this off of Wikipedia, and I'm just going to share the Wikipedia page. But basically, like this Mott Schottky equation utilizes the flatband potential, or people are solving for the flatband potential, and they're using EIS to get like
The capacitance.
the capacitance, the
Yeah.
space charge capacitance
Yeah,
of
that's the
of a
Mach-Schottky.
semiconductor.
That's what leads you. That's the Mach-Schottky equation that from which you plot 1 over the capacitance squared against potential, and you
Mhm.
get the flat band and the electron donor density.
Yeah.
ND and yeah.
So those are and your question and your question, Axel, was very much just like, what are these things used for? And I don't really know what they're used for, like why people care about them so much, because I'm not like a semiconductor physicist or semiconductor chemist. I imagine a lot of it has to do with solar energy or electrocatalysis. A lot of people are trying to find, what is the what is the space charge capacitance? What is the electron donor density? How much current do I get from a certain semiconductor? I think these are all quantities that we use to characterize and qualitatively compare, or not qualitatively, quantitatively compare different semiconductor systems, photoelectrochemical systems.
Well, to the question as well, just on the last point, and then we should move on.
Yeah.
But about what's the difference between flat band potential and OCP? Is it? And I'm sort of asking if you would know too, because my hunch is that this is correct. But is it correct to say that the OCP is more of a function, like you showed, of the references, of course, and sort of whatever stable thermodynamic equilibria you can reach for whatever specific amount of Faradaic or non-Faradaic processes are all in aggregate occurring, whereas the flat band potential is material specific. So, for example, one is material specific, one is like whatever the heck you have in your solution specific.
Oh yeah,
you know what I mean? So it's like you can have the same flat band potential for your silicon, p-doped silicon, whatever, right? That it has a flat band potential because it's a material property.
Yeah.
But then if you put it into sulfuric acid or KOH or a pH buffer, it's going to have a different OCP.
Correct.
But it's flat band potential, which is related to those principles you were talking about. That's not, OCP is more of that thermodynamic, and depending on what reference you have, that's, is that
I think
probably
you're right.
more accurate? I don't know if that flat band
you're right.
potential would change with any of those. I think it's more material specific.
Yeah, there's all kinds of like band bending stuff that happens when you like have an n-doped or p-doped thing and you put it in solution. And to my knowledge, it's like the atoms of the semiconductor near the surface are bending their potential, sort of say. It's something I haven't fully wrapped my head around, and I haven't talked to somebody. We need to get Alex Bredar back here and really like pick her brain on it. She knows this stuff really well.
Our good friend Alex Bredar at UNC, probably soon to be a distinguished professor somewhere.
That's right.
That's right. She we've had some good discussions about all this. She's tremendously insightful on the intricacies of semiconductor electrochemistry. It fascinates me.
It's interesting. So I'm just looking at some future. OCP under illumination shows flat band potential. Okay.
Interesting.
OCP
So
under illumination. Okay. Yeah. That's right.
Interesting. Yeah, there's definitely it appears Masa probably knows more about this than we do. Yeah, it's to be honest, that's why, as we've said before, if we don't know the answer, we're going to try our best, and then there's certainly things that we don't totally know. And this concept of flat band potential has been something that I have not totally and fully understood well. I did not really do semiconductor electrochemistry when I was in graduate school or postdoc or anything. I've only tried to gain as much knowledge as I can, in the last however many years working in our jobs as we have now, right? And so I understand Mach-Schottky as a technique. I understand electron donor density as et cetera. So anyway, good questions, Axel. Thank you for those. And I hope that we've at least done our best to illuminate. Get it? See what I did there? A little bit for you. Hopefully it was at least a little bit insightful. Next we have from AAR360. I could pronounce that one. Why does temperature affect the reaction that occur at electrodes apart from Le Chatelier's principle? That's a good question. Well, so affect the reaction. I mean, when you this is one of these examples. It's a little bit general. When you say affect the reaction, it's like what specifically, right? Like for example, like temperature might affect what the kinetics, the activation energy, it
shifts the potential.
Like there could be a lot of things you might be referring to, but but effectively, I know you said apart from Le Chatelier's principle, but it's like, in essence, some of the answer to your question is Le Chatelier's principle. Like, if it's endothermic or exothermic, heat
Yeah.
appears on one side of the equation. And so when you
Yeah.
increase the temperature or decrease the temperature, you're adding or removing heat, right? Which pushes the reaction in one direction or the other, right? And then there's also stuff like activation energy and, and there's Arrhenius
The Arrhenius
equation,
relationship.
right? The Arrhenius
Yeah.
relationship is to calculate the activation energy, or
Yeah.
right, and that's temperature dependent, and so that
It shows how the rate of the reaction changes as a function of temperature.
right, exactly.
Which is
So
always interesting.
yeah,
Because it's an e to the I find it interesting, the Arrhenius relationship, that it demonstrates the rate of reaction. Like, you just think like, oh, temperature increases, the rate of the reaction increases, but how? And it's like a e to the
minus EA.
it's like e to the minus 1 over t.
Right.
So when t gets bigger, it's only it makes an exponential,
a negative
exponential
So,
lower, which is just like,
yeah.
oh, that's how it
Yeah,
increases.
it's a bit of an odd relationship, but yeah, it's related to the Arrhenius relationship. That is an answer to that question, which is, I guess, a decent answer to the apart from Le Chatelier's principle, because again, like I said, one of the answers is if heat appears in one side of the equation, changing the temperature applies or removes heat, which drives the reaction in one way or the other of the equilibrium arrows or whatever. But the other is the Arrhenius equation, which describes how the rate constant changes with temperature.
Yeah. Hopefully that helps.
Hopefully that's a decent overview.
Yeah.
Without getting too much more specific. This one seems actually fairly quick to answer. It says, Muluken has said, I tried to electrodeposit a manganese oxide on carbon cloth from potassium, is that potassium permanganate, I think, and K2SO4 solution. And I saw that potassium is present in my sample along with the manganese oxide. How can this happen even at positive deposition potential? Because you almost certainly did not deposit potassium. You just have salt there.
No, yeah.
You probably just need to rinse your stuff better. So one of the things about working with almost any electrolyte solution is that it can take a frustratingly long time to rinse fully salt away. It's most likely just small. Maybe you did. Maybe you'll say, oh, I did rinse it. And it's like, just to give you one anecdotal example, which is not exactly your system, but just to give you an idea, like when I was in graduate school, I had to make these nickel different catalysts. Okay. And the precursor materials had like chloride, precursor or whatever you have, nickel chloride or nickel, nitrate or whatever it is. Okay. So you like cook it for a while, you boil it, you put it in an oven, whatever. The point is you get this material, but then you have to rinse it because there's residual salt that might still be there. And it's like, I quite literally spent days, I mean like 8, 9, 10, 11-hour days consecutively, like putting it in water, centrifuging, filtering, just waiting for water to drip out, rinsing, drying, over and over and over again. And after like 2 days, I would still see chloride coming off of the what's the word, the like the water coming out of this, is it effluent or effluent? The water that comes out of you drip water, it's like you rinse it with water and then like
it's like the elute and
elutant or whatever. There's a word for this.
It's the excess of
the dregs of the liquid that comes off.
Yeah, that's right.
Anyway, my point is that you almost for sure, because of the potentials that you recognized, did not likely form some like potassium complex. It's all, I mean, that seems really unlikely, and you seem to be very quite intelligent enough to realize that that's not likely the thing. You probably just have some salt that's stuck. I think that you're just going to have to try to rinse it more, and it might be frustrating, because rinsing it you don't want to, I don't know, physically and accidentally remove something that you electrodeposited, right? So it's tricky, but most likely if there's just some salt there.
Yeah.
I can't think of any other reason that might be there. And it might be impossible to get 100% of it out, but I bet if you rinsed enough, you would
Mhm.
remove most, at least, of the residual,
Yeah.
salt ions. So
Yeah.
anyway, most likely you're not winning a Nobel Prize for like newly discovered potassium reduction.
Yeah, that's right. At
So-
positive potentials.
Positive potential potassium reduction.
Yeah, that's
Because
right.
if you do, please include me in your speech
Yeah.
for your Nobel Prize. So yeah.
Looks
that's funny.
like we got Barry.
Yep.
Barry's back. Hey Barry, how's it going? Good to hear from you. Barry asked, what is the setup for 3-electrode photoelectrochemical H cell measurement, and how is it different than shining light in a normal cell? Oh, that's a great question. So we can draw just like very generally a couple of these things. So let's. I'm going to hide your question just because it might take a little bit of space. But if you can, let's see, just make sure people can see, and then just hide this. So we're going to be talking about like just different cell configurations. And so what a typical regular 3-electrode cell looks like. I think most people kind of have an idea. We have, say, some kind of beaker. It's got some solution in it. And then we have 3 electrodes, and I'm not drawing them in any particular great way or particular order. But oh man, this is bad. Oh geez. Oh geez. All right, this is a reference electrode. I'm playing. That's a frit, and this is just this is like a working electrode. So this is all right. So ref, and then counter, and then working. Oh man, this is ugly. But yeah, this is one of those things where it's like I should have made more space. Anyway, this is traditional 3-electrode experiment, and an H cell configuration for the majority of H cell configurations looks a little something like this. And I'll draw an H cell that looks kind of like the one that we have on our website. An H cell is usually characterized by having some kind of frit, some kind of separator or membrane between the two chambers of the H cell. And typically what happens is you will have a working electrode. And because it's a photoelectrochemical one, I'm going to make it look like this. And then you have a reference electrode that looks, I'm just going to make it look like this. There's a frit on the reference. So ref is here. And then working is here. And then you have counter electrode on the other side. So this is counter, some kind of coil. So this is the general configuration of most H cells, whether it's photoelectrochemical or not. And the goal for the H cell is that during an electrolysis, and that can happen in photoelectrochemical or just regular electrochemical experiments, there may be some species generated at the working electrode and the counter electrode that you don't want to have mix together. So you have a frit that slowly bleeds material from one side to the other, and it's very slow. It should be like, hopefully maybe like a drop or a milliliter an hour or something like that. Sometimes it takes longer or shorter. But ideally, there's a separator so that these two things are not mixing dynamically. But similarly, you can have any kind of configuration for shining light on this, whether it's just a traditional cell, or maybe you have a bottom illumination if your electrode looks something like this. So you can do that. And I would say the main difference in a photoelectrochemical cell between the H cell configuration with a frit and this one, the traditional 3-electrode, is that most of the time with 3-electrode systems like this, you're doing an analytical technique to learn something new. Say, get the flatband potential of your semiconductor material, something that somebody was asking about earlier. But in this kind of configuration, you're doing more of a bulk electrolysis type of experiment. You're like, I want to photoelectrochemically generate a species here, and then I want to take it to the NMR or the GC and characterize, the system, and I want minimum contamination from whatever's happening on the counter electrode side. So hopefully that provides some help, some kind of some advice at least on it. But please let me know if you have any questions, and if that made sense, Barry,
Made sense to me.
and hopefully the rest of our audience.
Let's see.
Okay, continuing on.
Animesh had another question about modeling, pseudo P2D, pseudo two-dimensional modeling. Wanted to know about this as a computational approach to simulate electrochemical behavior in lithium-ion batteries. I can't help you here. I don't know, actually. I've never done pseudo two-dimensional modeling of batteries, or perhaps I have, but I've done my own. So I have one publication from when I was in graduate school where it was studying material, its decomposition, and I developed a little, like, my own, mathematical model that would, in theory, capture the behavior of material, charging, discharging, and decomposition and everything. But I don't know that falls under this category, or that it was part of a bigger effort for this pseudo two-dimensional modeling, which seems to be a body of research or what have you, something like that. So I don't know that I can say anything more. I don't know. I don't really know that I can give you an overview. I don't know much about it. Sorry. Yeah. There's a lot of different kinds of modeling of batteries that people do. And empirical kinds of, take some data and empirically relate it to the temperature, state of health, state of charge, things like that. But I never really did much of the computational.
Yeah, me neither.
I was more of a practical. I built batteries, I tested them, and things like that. I didn't do a lot of modeling efforts and computer simulations and things. That wasn't as much my area. So I don't know a ton about it. I'm sorry. Let's see. Masa had a question before giving us good tidbit about the OCP under illumination, this flatband potential. Question was, is there a good reference showing how to choose the proper equivalent circuit for fitting EIS spectra? An EIS semicircle can be fitted with many equivalent circuits, and it's very confusing. So, to plug our own content, I guess I have a 5-part EIS webinar series on our YouTube channel. And in the second and third in particular of those, I go through a ton of different examples of circuit models that are used to fit data, many of which have semicircles, right? There isn't really a good answer to your question, and the reason is because it all depends on what is going on. So if you are in the unfortunate situation that you've got some setup and some system, and you're collecting impedance data on it, but for one reason or another, just practically, or because it's a bit of a tricky, complex system, let's just say, you're not really sure, like, microstructurally what's happening, and you're getting EIS data and you don't know how to fit it. I say unfortunate because there may not be a good answer. For example, should you use just a Randall's element, which is a resistor, capacitor, or CPE in parallel? Should you use an embedded model, which is like two of them kind of, embedded in each other? Should you use two? Should you use a Warburg short model? Is there diffusional element? Should you use a Gerrischer? Is there, some simultaneous irreversible chemical, first order chemical step occurring? The point of this is that there isn't really an easy answer. And because the answer to that comes with your, hopefully, ability to discern something about what's happening microstructurally on your electrode, something fundamentally electrochemically that's happening. which would allow you to pick the most appropriate model. In the absence of that, my advice to you is to just pick as many Randall's elements for as many semicircles you find, because that's like the simplest possible thing. So for example, if you really aren't sure like what's happening, like I just said, if it's unfortunate, you kind of are, I don't know if there's really diffusion. I don't know if I have a substrate in a film. I don't know if I have a chemical step or not. It was just like, if it's either impossible or just difficult for you to really kind of know for whatever that reason might be, then the simplest possible, like mathematically simplest and practically model that you can use is just a Randall's element, right? Just a resistor and a CPE in parallel for each semicircle that you have. Just add one of those, because that is the simplest way to capture a semicircle behavior, and it is the simplest way to describe a charge transfer process of some sort, which is what leads to a semicircle usually. Right. So that's the best advice I can give you is if you aren't able to sort of logically or what have you direct yourself to the appropriate model based on what you know is happening, and just use as many Randall's elements for how many CPEs and start there for how many semicircles you have, and then start there. And that might be the best way for you to at least get started, right? Until you're able to hopefully eventually learn some of the specifics about, oh, well, I definitely have diffusion here, and I definitely have this substrate in this film or something. And so that would allow me to utilize a more complex model of a specific type, the embedded model or what have you, right? That would more accurately capture what's really happening.
All right.
Welcome, Chris. Good to see you. You are a bit late. I'll be docking your pay, but don't worry.
Let's see. I think Fernando has a question. Fernando, I modified a flat surface SPE into a porous one. The EIS in ascorbic acid, SPEs didn't respond to, I guess, ferrocyanide, showed the RCT is 4 times lower in the porous one. How should I measure the electrochemically active surface area? That's a very good question.
Flat surface to a porous one. EIS and ascorbic acid showed 4 times lower in the porous, I assume, than the flat.
Yeah.
How do you measure the electrochemically active surface area?
It kind of sounds like 2 separate things. Like there are ways of measuring the electrochemically active surface area. But then there's also like, are you trying to rationalize why is the charge transfer resistance 4 times lower in a porous system versus in a flat system? I'm just trying to make sure, like, or is this one of those like trick questions from like high school where like they give you all this information, but they're really asking you like just one simple thing, and they want to make sure that we're paying attention and following instructions. But depending on what your SPE is, of course, the easiest is if you have platinum, and you just look at the hydrogen absorption region. But that might not be the case because not everyone's using platinum to measure things. There are a couple other things that you can do. One way is to use a well-characterized redox active molecule, like something like ruthenium hexamine, even though, ferrocyanide actually does stick to the surface a little bit. And maybe
it's probably
that's
better.
what
He says that they didn't respond to that. So perhaps they won't have to use ferrocyanide, which is useful, which is good,
Yeah. But there is a thing like, so you can do, there's many techniques, but there's like with cyclic voltammetry, if you know, say, the diffusion coefficient of the molecule, you can, and everything about it except for the area, you can then back calculate using the Randall-Sevcich equation. You can back calculate what the electrochemically active surface area is. You can also use a technique like chronoamperometry or double potential step chronoamperometry, which is good if you have something that you want to know what stuck to the surface, and like what came off. That's another like way of figuring out what the electrochemically active surface area is. But that's kind of the general approach. And I don't know if that's exactly what you want, because I can explain that a little bit more, or at least in a little bit more detail. So like, for example, this is a technique for, let me erase this. But for example, in double potential step chrono potentiometry, you're doing like you step the potential, you have a decay. That's not a great decay, and then you step it back, and then you have like another decay, and this is time, and this is current. So IT. And basically, when you have data like this, and you actually look at the total charge or the total current that's passed, the charge, if you integrate most of the area as a function of time, the total current is based on, I'm not going to draw the whole thing up, but there's like the Cottrell equation, which has to do with the diffusion. So there's charge. So all the charge in Q is from the Cottrell equation. And I'm just going to mention that it has a 1 over T to the 1/2 dependence. So this is like diffusion. Plus the charge of double layer capacitance. So we sometimes call that Q DL. But then there's also, they'll sometimes put this like gamma symbol, which is just like adsorbed. It's like the charge associated with adsorption of stuff that got stuck to the surface. And you can use this to either figure out how many molecules are on the surface, or this, because it's surface dependent, tells you charge per area, right? So you can figure out like moles per square centimeter or something like that. You can usually figure out how many molecules get stuck to the surface with this guy. So some people will do this double potential step chronoamperometry experiment where they pick one potential that reduces everything, and then another potential that oxidizes everything. And then when you take the difference in the charge between, from the forward step and the reverse step, the difference is whatever got absorbed onto the surface. Because ideally, the double layer charging is equal between the two, and the diffusion charge is also equal between the two. So that's another thing that people do to figure out like number of molecules on the surface, the area of your system, the electrochemically active area. But you got to do this for a molecule that diffuses well and behaves well within the pores of your system. So that's kind of that is one way to possibly go about it.
The other just general comment I'll have is that this is actually one of these tricky things, right? The most common measure of ECSA is just done with platinum, because the hydrogen adsorption desorption region has a very well documented and well known specific capacitance of 210 microcoulombs per centimeter squared. So what you do is you just measure the platinum, the charge of your platinum adsorption desorption region, and you divide by 210 microcoulombs per centimeter squared, and you just get the number of centimeters squared, and that's your ECSA. The tricky thing is that with anything else, I don't know of other, there might be some other examples. It's like, I just sort of briefly tried to look about like, is there a specific capacitance of like ruthenium hexamine, whatever, but it's usually more electrode dependent. So this is like platinum specific. And with you, I'm supposing that your SPE that you've made to it like a porous microstructure is not necessarily platinum, so this is not applicable, right? And so I think that typically with other materials, people tend to to get the ECSA, or at the very least the like active surface area, they do things more like physical techniques like BET, Brunauer Emmett Teller, which is a method where you basically stick your material in this it's an apparatus, right? It's a testing procedure. It absorbs nitrogen onto the surface. It measures how much leaves, and it gives you an estimate of the meters squared per gram. And so like what you would do in theory is you would basically take your porous one, make your SPE the way you would normally make it, like scrape the active material into like a little crucible and run it through BET, and you would get the specific surface area. And that would be what you would in theory use as what your ECSA is. But that's also more like geometric surface area. And so you, and this is the point that I'm making. I think that what's often done with electrochemists is that when it isn't something as simple as platinum with the hydrogen adsorption desorption, phenomena, a lot of times you're sort of forced to make an assumption that if you can get the geometric surface area of your porous microstructure, again, either through BET or like mercury intrusion porous, what is that? MIP is that? I'm not sure if it uses the acronym or something like that, but there's like porosimeters or or BET, whatever. These are methods to get specific surface area of materials, either its surface area or its surface area per mass. You just make the assumption that surface area is also the electrochemically active surface area, which isn't always the case, of course. Otherwise, I mean, I do think that it's like what Alex said, is that you might have to find a way, and I apologize, this isn't tremendously specific here, like what equation do I do? But if you look at like the Randall-Sevcik equation, right, you could imagine doing CVs, right?
Yeah.
And so this equation here is a relation of the peak potential that you get with a whole bunch of stuff. Yeah, the peak current, excuse me. Yeah, thank you. Yeah, peak current. Right. So you do a CV, you get a peak current at some scan rate, which is this nu or whatever that is. Is that nu?
Yeah,
I always mix it up.
It's nu, and they always.
I always mix up nu and
a V.
And yeah, no, but it's upsilon, I think, actually.
Oh,
our colleague Tim is always very up because I would draw it more like a V, which is like nu.
Yeah,
and he's like it's upsilon. It's more like a U.
Oh,
I think it's a thing.
Oh, interesting.
He's very adamant about this.
Yeah,
I don't care, which makes him more mad, which I think is funny.
Yeah, that's right.
Anyway, whatever. It's the scan rate.
Yeah,
right. And so, if you do something like ruthenium hexamine, it's a 1 electron, N is 1. Okay, R and T are what they are. Faraday's constant. What the concentration of your thing is. Basically, all that's left is the surface area and D. Now, normally what the surface area, you're assuming what your surface area is, and you're getting a measure of D at different IPs versus whatever, and you get D from like the slope or something like that, right? But in theory, if you do get a measure of D from the Cottrell equation, like Alex was talking about, or something like that, if you can, or if you just want to use a dummy value of D, like look up what the diffusion coefficient of your electrolyte is, and just say, this is about 1 × 10⁻⁵ centimeters squared per second. Like maybe that's, then you might be able to instead just solve for A, either at one particular scan rate or do a bunch of different scan rates and solve for A from the slope. Like that, I don't know how accurate that is, to be perfectly honest, but it might be a way for you to back out the area and you would infer that area being like the electrochemically active surface area because it's directly related to peak current. But that is at least an electrochemical way to do so. When you referred to your impedance data and your charge transfer resistance, I think it was being smaller. The charge transfer resistance being lower. I mean, I guess that's not necessarily surprising. If you have a more porous electrode, you have more like readily facilitated access to surface. There's a higher surface area, so it's gonna do more. It's gonna do better, charge transfer, right? And so the resistance should be lower because it might happen more easily if there's more preferential sites or something like that. You look dubious.
Yeah, I look dubious. I'm just like, then I was just like, I would just make the most porous thing on the planet.
Well, that's why people are looking at microstructure all the time. Improve, like this is why nanomaterials basically exist in a nutshell, because nanomaterials gives you tremendously high surface area. This is why people are looking at nanopores and nanorods and blah blah blah, because it increases the surface area. and the surface area gives you more current, lower resistance, better, better activity. That's one of the main reasons,
Yeah,
in general.
I mean, when I think about RCT, I think about like I think of it as more of a thermodynamic thing. It's just like, okay, when you change the potential, like I understand changing the potential and changing RCT. You've made it so that the resistance for the reaction to occur lowers.
That's right.
And so for mine, I'm like, all right, well, it's
means the current goes up.
thermodynamic.
Means the current. I mean, if you just look at it like Ohm's law, it's like everything I just said.
Oh, yeah.
Right. Think about it the most basic way you can. V equals IR.
Oh, okay.
If R goes down, I goes up.
Yeah.
For
Okay.
for the same potential. So it's like what I just said is just another way of saying the same thing, where it's like if I have more surface area, I can do more of the thing.
Yeah.
And when I do more of the thing, I get more current.
Yeah.
That's just more electrons flowing to do the thing,
Yeah.
to react to the thing, to redox the thing, whatever.
Yeah. Yeah. That's right.
So that's just lower resistance. This is just Ohm's law. It's just proportionate, right? So I would expect R to go down when I have a better.
Okay. Yeah. And R is going down because I is going up.
Right. Yeah.
Yeah.
You could say either or, right? I is going up because R is going down, or vice versa.
Yeah.
Right.
Yeah.
Exactly.
Yeah.
So that to me is but the
there's more active sites on the.
I suppose
the
for
porous
calculation
material.
of the ECSA, the resistance might not be as useful as perhaps the capacitance. I'm just trying to think, because it's like if there's again, it's more like you don't have a BET in your lab, so that will prevent you from getting a physical measurement. I'm just thinking abstractly here, but it's like, again, it's if you can find like this might require some literature study, but it's like if you can do like something simple, like Alex said, like ruthenium hexamine, or something
that's also similar to what you're studying in size.
Yeah, perhaps. But it's like if you can find if there's a system that has some kind of specific capacitance, like is there a specific capacitance of either the material or the reagent? And again, this might require a literature search because I don't know 100% of this, but it's like if you can find something that has like this many farads per meter squared, like you can find stuff where you get, like I just tried to look for ruthenium hexamine, for example, just and I'm finding stuff that's not what I want, but for example, just a quick like ResearchGate, Google Scholar is like specific capacitance of like ruthenium oxide is not what I'm looking for. But the point is that people report this many farads per gram, et cetera, of a specific material. So what you might be able to do is find like, well, the theoretical specific capacitance of your material, if it's graphite, if it's whatever, is X farads per gram. Then instead of the RCT, what is your capacitance? Because if you have a capacitor, either as part of your Randall's element or just a standalone capacitor, you'll have to figure out which one you're using, I suppose. But you'll get a measure of C basically, and that's some amount of farads. And so that farads divided by specific capacitance gives you either a mass or an area. And maybe that's related to the ECSA in some ways. If it's mass, it's a little tricky. You'll have to know the density or something of your material. You'll have to do some unit, stuff. Get the density and then figure out you have to do some geometric math, which isn't hopefully too difficult. But the point is that might require some literature research. But in essence, I'm thinking that the specific capacitance rather than the charge transfer resistance would be in some ways tied to a way to use the EIS data in particular, in addition to the other ones that we talked about, like Alex was talking about the chronoamperometry or using the Randall-Sevcik equation or something of that nature.
Yeah, I actually think that what you said about the Randall-Sevcik equation is probably the best way.
Yeah, maybe
to go about it to calculate the ECSA.
Yeah.
So
I think so. My only hesitation is that that is also making assumptions like the peak current. There's background current that might convolute the signal. So how accurate is it? I'm not going to say it's like perfectly accurate. That's the thing. There's some confounding stuff here.
Yeah.
Right?
but that's even just using the Randall-Sevcich equation in general. Like,
Yeah.
even if you weren't like, even if you were trying to calculate diffusion coefficient, you gotta get rid of the background current and all that stuff. So,
Yeah.
so if you use EIS or a rotator or something, or use another technique to determine the diffusion coefficient that isn't as dependent, like a rotator, there's little to no influence of the double layer capacitance in determining the diffusion coefficient using a rotator. So you can get a, so and it's a steady state measurement too. So I always think that the rotator is a very good way of determining the diffusion coefficient independently and perhaps more accurately. And EIS is also very good too if you have a Warburg element.
Yeah.
And
the Warburg element can be used to independently verify the diffusion
Yeah.
coefficient. Then you can use that in the Randall-Sevcich analysis.
Yeah. That is right. Of course. Well, maybe EIS. Yeah, I guess all of these assume some level of knowledge of the area of the electrode. That's probably
Yeah, but in theory, it should be easy enough to know the geometric area, right?
yeah,
Planar, like, I mean, it's porous.
Yeah.
So in reality, it's like,
right.
know.
But but yeah, if you use a planar electrode, that's where you have the geometric area, and you know the diffusion coefficient from that, you can then use that diffusion because the molecule diffusion is still the same, regardless of whether it's a porous material or not.
Yeah.
Of course, moving through the pores is a different story, but I'm assuming it's not like you have some massive frit or something like that.
Yeah.
We're making a lot of assumptions because we don't know
always
everything about your
making
system.
assumptions. That's right. Yeah.
Yeah. All right. It looks like there haven't been any questions on Twitter, which is fine. We definitely have some viewers on Twitter, which is nice. So thank you.
Thank you for
Twitter viewers
liking and sharing and
retweeting
and whatnot.
Of course, it's called X. Not
yeah.
Twitter,
I don't think I can ever call it X.
It's gonna take a while.
It's gonna take a while.
It's gonna take a while.
But even now, people still say Twitter X. Like they sort of say whatever.
Yeah.
And because I'm not trying to have any kind of a bigger conversation here. Just that Twitter is a good name. Like, it's an easy name. It's sort of like it's memorable. You remember Twitter. Like, everyone has been saying Twitter for years.
Yeah. Oh, I mean,
I can't get used to the new name. I can't. I still call it Twitter.
Yeah. I mean, it's one thing. Like, a company has reached a certain level when the company name has become like a verb.
A verb, exactly. Like you Google
that.
something.
You Google something.
Yeah, you need a Kleenex if you're in the US. Tissues are
Yeah.
Kleenex, right? That's became
that's a brand
synonymous. Yeah, exactly. It's like I tweet something.
Yeah.
The company name has become a different part of speech.
Yeah. Yeah.
That means you've made it.
That
right?
means you've made it.
That's a pretty interesting turn. Yeah.
Yeah. So far there's no other questions. We can hang out for a little bit.
Yeah, we'll hang out for just a little while because there are sometimes a rash of questions in the second hour. We kind of went. We had a ton of questions, and we kind of went through them all.
Yeah.
Here, which is fine. So we'll just shoot the breeze. So how are you, Alex?
Oh, I'm good. We were just at the MSR or MRS.
Wow, that's a Freudian slip.
We
were at the Wave Vortex conference.
The Wave Vortex conference.
It's
Yeah.
like, just name every part of the catalog.
We're at the Material Research Society conference in Boston.
Yeah.
Just yesterday. So we just flew back.
Yeah,
yesterday.
I'm totally jet lagged.
Yeah, and
yeah, for those we're on the same time.
We're in the same time zone, so
that's like one of my favorite dad jokes. I can't help it.
What, totally jet lagged?
Yeah, I'm jet lagged from flying within the same time zone. Like anytime.
Oh yeah.
Like we're in the East Coast of the United States, so we're in North Carolina. And for those who aren't really maybe aware of the geography of the United States, that's normal. But like Boston, Massachusetts is on the same East Coast. You just fly north for like an hour and a half.
Yeah.
So every time I get back, if everyone's like, "Oh, how was it?" I'm just like, "Oh man, I'm so jet lagged."
Yeah.
it's my favorite. It's my favorite travel related dad joke. I love it. I love it so much, and I can't stop doing it.
Yeah.
Like I need an intervention. Someone needs to help me.
Oh no.
Because I'm addicted to just terrible jokes.
No, terrible dad jokes are great.
I heard a good one about I heard a good one the other day. So if you have children or whatever, some people will say, what's the worst part about having children? And it's like, oh my gosh, it's like my house is just so full of, sorry, it's going to get graphic here. My house is just so full of like pee and poop and puke and stuff. And then I brought kids home.
Uh,
But how do you like that?
oh, that's good. Everyone here's a researcher. They're not,
know.
they're just, knee deep in EIS and CV.
They're not
and
knee deep in
chrono-
diaper changes.
Yeah,
I hope.
Yeah.
Enjoy your diaper free life for a while, and then have kids
And
and,
then
and,
kids.
and enjoy the
Parenting.
never being fully clean again.
Be fully
something.
clean again.
Oh my
Yeah.
gosh.
Yeah.
I
that's
do
funny.
love me bad jokes. I can't help it.
I do wonder if anybody here, I think, I don't know what the population of our viewership is, but it was recently an American holiday. It was Thanksgiving. And so I wonder if anybody had a good Thanksgiving or a good holiday. I don't know if also we're entering into a holiday season as well here in the
Yes.
States.
Yep.
So within a few weeks, it'll probably get really quiet. We may not have as many Ask Us Anything live streams, but we're
Or
going to try to go as
Or we'll
regular as we
maybe
can.
start it, but if nobody joins, we'll be here for a shorter period of time. Or maybe it's super busy because maybe people don't take holidays because you're all in graduate
Yeah.
school and you're not allowed to have a day off.
Yeah.
I would assume that's the case for a lot of you.
Yeah,
I don't know.
That's true. All right, we just got a question. Let's see. We just got a question from Gilberto. Let's see what he says. Hi guys, just the other day I was electroplating gold onto copper using potassium cyanide solution and stainless steel as the anode. But the steel got corroded very badly. Perhaps you know why this may be. Yeah. We can I can absolutely perhaps describe to some degree what I think is happening, Gilberto. So
Got oxidized.
it got oxidized because
You're reducing it.
because in electrochemical
I think what's
systems-
surprising is it's stainless steel. I guess that's still possible, but you'd expect it with regular steel more so. Stainless steel is a little more resistant to, hence the name stainless. But yeah.
Yeah, I guess I
Not
mean
to steal your thunder, please go ahead.
No, but I'm just making an assumption. I'm assuming, Gilberto, that you've got some working electrode, and I'm just gonna make a little circle here, and you're just trying to plate stuff. You're just trying to get some plating going on here, reducing, getting some electrons and just reducing stuff on this working electrode. But you also have a counter electrode that's like stainless steel, right? Stainless steel. And this is your counter electrode. So these two guys are connected by like some kind of circuit, like a power supply or something. And if a reduction is happening on this electrode, an oxidation has to be occurring on this electrode. And I know you have like potassium, cyanide in here, but basically, if anything plates on this side, something else has to be happening on this side. So if there's an oxidation occurring, like, yeah, electrons are leaving here. Iron, the iron in your stainless steel is turning into iron oxide. And even though you might have a reference electrode, you didn't specify that, but you may have a reference electrode somewhere. Reference electrode doesn't really care. I can't draw reference electrodes today. Just call it going this to like a voltmeter or something like that. But like, your reference electrode doesn't really care. There may be a low potential between these two, but there may be a huge potential between the working and the counter electrode. This is the compliance voltage. So you could even do this during your electrode plating, take a voltmeter and just touch the, the ends here of your system. You have maybe a little bit of brass that's exposed for an electrical contact, and maybe a part of the steel that's not in solution. Just put a voltmeter between these two, and you'll find out, like, oh man, there's a huge voltage between these two, even though the voltage between the working and the reference is relatively small. So just keep that in mind. That is my hypothesis based on what you mentioned, as to why, what might be happening.
And what I would say, just as an addendum, I suppose, is that number one, if this is a problem, then use a counter electrode or an anode, whatever, use an alternate, the auxiliary electrode, that's something, one of two things or both, that you don't care about. Because if what you're doing when you're plating gold on your copper, or vice versa, I forget whichever, I think it was gold on copper, is requiring a relatively large negative potential, or current, or both, it's going to, as Alex said, induce a equally or larger positive potential on the other one, which is going to oxidize, corrode, rust, whatever, in some manner, right? And this is actually quite common that you do see, even like in people that plate, like for the other example I have is like people plate copper on platinum, for example. And when you do copper plating and stripping, your counter electrode is undergoing the same thing in the opposite way.
Yeah.
So it's like when you're stripping off your copper, it's plating on the counter electrode. And so what people often do is they separately treat their counter electrode chemically by like dipping it in some solution that like dissolves it off afterwards. Cause you end up with this copper sheen on your,
that happened to me once.
Yeah,
It's the same
exactly.
mistake.
We have a customer, for example, that does this. They regularly use the platinum, counter electrode for this thing. And after all of their tests, the platinum counter electrode's brown, or, or whatever the color of copper is. I don't know how to describe it. It's copper colored.
Yeah,
right.
That's right.
And they have it's either piranha solution or it's some other, acid, something or whatever. And they have to dip the counter electrode in that every time to remove it. So the point is, you can't get away from having your anode, your counter electrode, do an equal and opposite or something. So you can either use, if you don't want the stainless steel to like corrode or just get obliterated, use something else that you don't care if it gets destroyed, or use graphite, or use something that is less likely to actually corrode. Like graphite will probably not get destroyed. It'll probably just oxidize happily, whatever it's doing. And then if what is happening over there, you're worried about it, you're going to have to use a separated cell or a fritted isolation tube for the anode, for the counter electrode. Because then at least if it's corroding, if it's, getting blasted away while you're doing your gold plating, well, it's happening separated, and it'll get that separated cell for the counter anode, whatever, or the fritted, isolation tube might get clouded, it might get rusted, it might get gross, but it's separate, and then you can just deal with it afterwards or dispose of it. I mean, it's probably costly and maybe not ideal to be like constantly using a new counter electrode every test, but this is a thing, right? They call them sometimes like sacrificial
electrodes or agents or something.
Yeah, exactly. Right. I don't know exactly what the term is for it. Maybe it varies, but like a sacrificial anode or a sacrificial counter electrode is a thing. And it's in cases like this where you have to apply this highly reductive, sometimes it's the opposite. If you're doing an anodization technique, it's a very highly oxidizing thing. And that means you're highly reducing the other thing. And sometimes that just wrecks apart your counter electrode. And so you just use this rod of something that's like it might dissolve by the end of the test. It's or largely dissolve, and it's like you have a sacrificial counter electrode for your test, and you just got to use a new one each time. So that isn't unusual, and so just consider some of those things, I guess.
Hopefully that's helpful to you.
Looks like Tafara needs advice on what Ph.D. route to take. So I would say don't.
Yep.
Sorry. I told you I like dad jokes. I can't help it. You're just going to have to, if you want advice on electrochemistry, you have to put up with the dad jokes. It's just what happens. Let's see. Studying porosity of lead acid battery electrodes using a synchrotron.
Okay.
How would you do that using a synchrotron? That's interesting. Usually synchrotron is like X-ray or X-ray absorption or things like that. It's interesting. Or modeling for interaction of microcapsules in lithium-ion batteries. Well, first of all, I'm partial to lithium-ion batteries just in general. So my actual honest answer to you is it depends on whether you are the type of person personally who enjoys laboratory work or computer work. Really, that's if these are the two topics for you to choose from. My guess is that you should be more inclined to pick the one that's conducive to what you prefer. Like if you really just enjoy cranking away at like coding and sheets, like modeling is going to be very much a solo sort of activity, you know, modeling, and like people who do like DFT and these kinds of things. Like you're just kind of at a computer, you know, doing MATLAB or doing maybe another what's the program? There's some other programs, you know, like
Oh, for coding, like
yeah, and
Python or something.
what is it?
Oh, Python,
Yeah, but
Okay.
but also like
like the coding language.
there's
or-
one I can't come up with it. It's like that renders models, you know, will render the three, you know, and I maybe
Yeah.
or maybe you're just writing your own code in Python and then, you know, compiling
yeah.
it. The point is that like the modeling route for a PhD is helps, like if you're like, I'm just, again, for example, if you're fundamentally like introverted and you don't really like being around people and you kind of prefer solitary, I'm serious, you know, I'm not, that's not me. Like you know, like Alex and I are pretty extroverted. We like talking with people. We like visiting people. You know, I don't, I'll speak for myself anyway,
Yeah,
but I don't really prefer working in isolation for too long if I can avoid it. You know, I like social interactions and things like that. So a purely like, you know, sitting in my office, just cranking away at a code and modeling all day sounds like misery to me. But some people are like, I don't have to see another person for days on time. That sounds great, you know?
Mhm.
So that, apart from the interest of both of those projects, I guess. ComSol, thank you, Chris. That's the one I
Yeah,
couldn't think of. Yes,
ComSol.
that's the one I was thinking of.
Yeah.
Chris, you and me, we're in sync. ComSol is the one I was thinking of. That's what. Yes, that's exactly what I was saying. There's other similar versions of ComSol, but that's the one that I'm aware of. I guess people still use ComSol, I think. Anyway, so anyway, that's my answer to you. You know, it seems based on your explanation that if you're doing porosity studying and using a synchrotron and all that, you're going to have your hands much more dirty in the lab, more, you know, preparing stuff, wet chem, whatever. And if that doesn't feel like something you want to do as much, then I would go for the modeling one. Otherwise, I would personally pick the one that gets me more in the lab, more busy, more with people, and etc. I don't know. What do you think?
So there are a couple of things, and I agree with you. It depends what you want to do, because there are things that sound great on paper, just as what you said, like studying the porosity of lead acid batteries is like, you know, that's really cool. I get to do this thing, and present about it, you know, and write papers on it. But like every day, like what you do every day is going to be different. Like I think I was thinking about this earlier. Like bodybuilders get up on stage and present, and they look great, and they have muscles, and they're huge, and they're oiled up, and all that stuff. But like every day of their life is just going to the gym and like eating rice, chicken, and broccoli like every day at nauseum. And you know, you don't see that, right? And similarly, if you're going to do a PhD that's more experimentally based, you're going to be in the lab every day, like a lot, right? That's what your day is going to be like. If you're going to do more modeling, you're going to be in front of a computer screen more often and coding and stuff like that. So yeah, figuring out what you want to do like every day, and the people, I would also say the research group that's doing those things should be a big indicator, because I think you can be successful in either one of these things in life, right? But the people who you work with, your advisor, how you you know, work well with them, you know, you might hate modeling on a computer, but the guy who runs it may be the coolest person, and you may totally change your life type of thing, you know, and vice versa. You know, the people really also make a big impact on the kind of research that gets done. Another thing that you may also consider or think about is what you want to do after graduate school, which is, do you want to be in the lab doing further battery research experimentally? Well, having some experimental experience is good. Even in industry, it's also like very good having that background. But you also can, you know, if you learn how to code, you could apply that to many, many, many different types of situations. You know, you could model a lot of things. So those are kind of my 2 cents on which route to take. A lot of it depends on the systems. Another thing I'll mention that's very specific is synchrotrons in particular are, you know, really national labs are the places that have these things. There are not a lot of them, which means that when you do experiments with a synchrotron, it's relatively unique data that
Yeah.
you will get. Like, not everybody can do this. It's not like every university has an NMR and every university can get an SEM. Like, cost wise for a university, like an R1 or even an R2 or R3 research institution, you can get those things. But synchrotrons are much more rare, and you will and beam time on a synchrotron, because I know some labs that have used synchrotrons for X-rays and stuff, and when they have beam time, because you have to book this stuff in advance, sometimes you're at a national lab for like 3 days straight, like sleeping there, because when the beam is on and you calibrate and you get everything set up, like, you're on and you're just trying to collect as much data as possible in a short period of time. So, and then you go back, and when you're done, you have to evaluate it, do some stuff, rethink about your cell, rethink about the lead acid batteries. So that's another aspect of just like practically you will run into some times where like you have to work at an extreme intensity for like short periods of time when you're doing synchrotron work.
And
So,
at weird times too.
and at weird
Beam lines
times.
24/7. You might
Yeah.
end up with your beam time between like 1 and 7 a.m.
Yeah,
And
that's right.
that's when you have to do it.
That's just when I have to do
It's
it.
a different kind of life.
Yeah,
for
yeah.
sure.
So that's another thing. Hopefully that's helpful. That's my 2 cents. I
Okay.
hope that was helpful.
Energy Eve says that we are the EChem gang.
Yeah.
Does
Thank
that
you
mean
for
we need
joining
like
us.
graffiti
Yeah, that's right.
symbols or something? Yeah, I guess so. You're leaving Ph.D. to join industry. That's what we did. Well, I guess
Yeah,
not. Well, we
sort of.
finished our PhD and then joined industry anyway. The
Mhm.
point was that we left academia, which in my opinion is the correct answer. Yes.
Mhm.
I wasn't much for staying in academia, but nice for you to join us. I think this is a cool kind of just question. Where do you see the next breakthrough in electrochemistry? Depends who you ask.
Yeah.
Right? Because everybody's sort of tunnel vision for their research and things. I would
Mhm.
I don't know. I really don't. I don't know sure how
Yeah,
I
none
how
of
I
us
could
do.
know. I have 2 answers. The first is generally speaking, it's batteries something, because batteries are the present and the future of
Mhm.
electrochemistry. It's the more and more folks are doing batteries research. It's what drives all of our electronics, powers most of almost every electronic device that's used is batteries. So it's probably in the battery world. And then I'll just say that, because we were just at the
Yeah.
where you least expect it. Yeah, that's right. That's where it's happening, where you don't expect it. But that we were just at the Material Research Society conference, as we said, in Boston this week, and it's not all electrochemists, to be fair, right? So it's not there's the International Society of Electrochemistry, the Electrochemical Society itself, American Chemical Society. MRS is not all even chemistry, to be honest. It's material.
yeah.
They're people studying materials for all kinds of things, and so we
Yeah.
only hear a subset of those folks who are using chemistry or electrochemistry. To
Mhm.
be fair, however, there are a lot of people looking at different kinds of batteries, solid state batteries.
Mhm.
Sodium and zinc in particular seem to
Mhm.
be like up and coming battery chemistries for a couple of reasons. It's a little less toxic. They can use aqueous materials, and they're more easily and sustainably sourced than the materials required for a lithium battery. Basically, in short, the materials that are used to make lithium batteries, they're not easy to mine from the earth,
Mhm.
and in some cases, perhaps there's some ethical considerations regarding the extraction of certain elements and materials that are required for mass scale production of lithium ion batteries. And in essence, to the best of my knowledge, a lot of materials like zinc, for example, are cheaper, easier to obtain, and things
Mhm.
like that. So there are folks who are heavily pushing for different battery technologies along those lines to I shouldn't say replace, but at least supplement some of the battery
Yeah.
usage, right, in the commercial space,
Mhm.
whether it's for stationary storage or consumer electronics or EVs or things like that. So anyway, those are my answers. Basically, in short,
Mhm.
it's in the battery world somewhere. Whether it's any of those things I said, I don't know.
Yeah,
I don't know if
I
you had a
agree. We
different
were
answer.
at the same conference, and I remember hearing this guy talking about zinc and sodium batteries is the next thing.
Yeah.
From lithium.
I called them a cult
Yeah.
because I'm a lithium person. I study lithium, so I've been hearing folks talk about zinc and sodium batteries forever. And
Yeah.
well, I don't have a sodium or zinc battery in my phone, so ha.
Yeah.
I'm just kidding.
Yeah.
There's this kind of fun. I hopefully see it as fun. I don't. I
Mhm.
hope I'm not misreading the room, but I find it to be kind of a fun interplay between the folks doing zinc or sodium and the folks studying lithium, because lithium kind of won.
Yeah, yeah.
Lithium are everywhere, right? So,
Yeah.
and the zinc folks are and sodium researchers, let's say, are often touting how great their technology is and
Mhm.
try and there's a bit of a rivalry, kind of, almost in some funny way. I
Mhm.
think there's a lot of
Oh.
that happens, and I actually think it's in some ways healthy, because we push each other to make better materials, and humanity improves when we have
Yeah.
better
Yeah.
research and
Mhm.
better energy storage, and that all of that's good in some sense. Hopefully we don't actually do terrible things to each other,
Yeah.
but
Well, actually, I think you said it best actually at the MRS conference, which was that the answer is not going to be one thing. It's going to
Yeah,
be
it's
a
not.
bunch of things, all all uniquely able to solve a specific problem that no one magic molecule is like the key. It's going to be a lot of different things
Yeah.
that help us with
Yeah,
solving problems.
I think that does tend to people, I'd say in general, like to have simple solutions to complex problems.
Yeah.
And frankly, there's usually not such a thing. There are cases where, oversimplification or reductionist views on some, I'm just speaking generally,
Yeah, yeah,
I suppose, in some cases you can sort of come up with a simple solution to things. It's the Occam's razor, right? Like the
Mhm.
simplest solution should be used in the absence of anything else. Like if you can use the simplest explanation to just to explain something, whatever. But as far as the energy situation for like humanity
Mm.
writ large, it's like it's so multivariate.
Yeah.
It's a multivariate problem. Countries and people all around the world, that how could it, like, if you would just be like coal, nuclear,
Yeah.
wind, I sound like
choose one.
I sound like
Yeah.
Captain Planet, like
Yeah, that's
wind,
right.
water, heart. Like if you're just to pick one, it's like there's no way that you could do that, right? Someone who's living near a giant waterfall should probably use hydroelectric
Yeah.
power, and
Yeah, that's right.
and other folks who live in a desert climate are going to have to use a different kind
Or
of energy,
solar, or
whatever. Yeah,
a lot
exactly.
of wind.
Yeah, right. So just, I just think that we have to be open to being very
Mhm.
heterogeneous solution to the energy problem. So yeah,
Yeah.
I do think that's probably true.
Energy has another kind of follow up.
Yeah, I was just saying sodium has made some. I did see something. Someone sent me, just out of context here, but someone sent me an article about a sodium battery breakthrough. I do think there's been some breakthroughs in sodium
Mhm.
battery. Again, I don't know. I've heard, and we heard this at MRS. These batteries are perhaps more likely to be start getting implemented into like stationary storage, as
Mhm.
opposed to like portable consumer electronics and things like
Oh,
that.
mhm.
So that is a perfect example of this heterogeneous whatever
Yeah.
solution, where it's like, oh well,
Yeah.
we can use lithium batteries for phones and laptops, and we can use sodium batteries for like energy storage for buildings, or I don't know,
Yeah.
whatever.
Yeah.
Like maybe that's
Maybe
a
that's
good
the way.
answer, right? I think that could be what it is. So yeah.
Uh,
Energy Eve is asking about
yeah.
how we started this or something.
Yeah. He's just asking what prompted this live stream event. Yeah, we're both we're both electrochemists who work at Pine Research Instrumentation, and we get a lot of questions from people just about fundamental electrochemistry questions. And these are through email and through our YouTube channel, through webinars. And we just get a lot of these. And sometimes it makes a lot of sense just to let's just host a Ask Us Anything about electrochemistry, where we
Yeah.
can try to teach people, because there's always a concept that some people don't they need to talk to somebody about like what this is and what it means, and we try to help as best as we can.
Yeah.
So that's kind of what prompted it.
Honestly, it was somewhat of a harebrained idea that each of us sort of, I don't know which, it doesn't matter at this point, who cares? One of us or both of us sort of had, like brainstorming the future. Cause really, actually, I'll just, he'll never brag about himself, but Alex is responsible for the majority of our YouTube content over the last 6 years or so. I don't know, pick a number, right? And most of the videos you see on our channel, if you're on our YouTube channel now, like after this or now, if you're ignoring me, check it out. Check out all the videos. Like it's all Alex, right? You can see him before he even had a beard. It's crazy.
Oh yeah.
He's like a whole different person.
It's like a baby.
Yeah. He weighed 8 pounds less because his beard is so luscious.
Right.
But yeah, I mean, it's just all of the YouTube content, and it's like obviously in a post-COVID world, and where we've been and where we are now, it's like we realize that most students have phones and are, this wasn't exactly the case when we were in graduate school. Heck, even 10, whatever, 15 years ago, whatever it's been,
10,
55 years aago. I'm really old. No, but
it's been a while.
Yeah, it feels like it's been a while. But
next year it'll be 10 years for me. 2014 was when I graduated.
I finished in 13. So yeah, it's been 10 years already. So,
hey,
10, it was 10. Yeah, 10 plus years ago.
Yeah.
But it's like I didn't have that, even some of these resources. And so it's just always seemed, I don't know, evident that students in the lab now often feel lost. They're trying to find resources. And it's like we've been ramping up our efforts together with YouTube and whatever. That's why we launched a podcast as well.
Yeah, this is actually answering this next question.
Yeah, what's the future is a podcast. That's the future.
Well, the future is hoping to produce as much media on the platforms that people are at, right? Like,
yes.
We don't put very much stuff on Facebook because very few people who are just on Facebook who are of our demographic who need the help. But a lot of people
it's not a scientific platform.
It's not a scientific platform. But if and a lot of students listen to podcasts. That's the other platform that we're branching into. So we're trying to be where the community is at, and really kind of help them. And yeah, I got goals. Neil wants to make more webinars. I want to make more videos. We're trying to put out a lot of content. That's really the goal, and our vision of the future.
Yeah, I mean, it's honestly, this live stream itself was, I had high hopes, but perhaps cynical expectations that have been greatly met and exceeded. I mean, this is our 32nd one or 30. Yeah. We've been doing this for like almost a year.
Almost a year.
Right. It's been almost every Friday. We've taken some off. And, last time I did the math, there's about 52 Fridays in a year.
Yeah.
Right. So we've been doing this for the better part of 8+ months.
Yeah.
And I mean, we don't get 5 million people. There aren't 5 million electrochemists in the world, but we've been getting enough of you joining us every week, and we really appreciate it. Because our first idea was like, let's just go live on, we picked a day and a time, and we're like, let's just go live and see if people come and ask us questions.
Yeah.
And if they don't, we'll just talk about movies or something for an hour, and then we'll never do this again.
Yeah.
And we've been doing this every week or almost, and people keep coming and asking, and it's been great. In fact, I remember the first week, however long ago, we were practicing, like we're setting this thing up, and the format has changed ever so slightly here and there, but we're like, well, we have to see how it works. So we go live with no announcement, nothing whatsoever. We just randomly go live on our channel.
Yeah.
Just to
see,
troubleshoot the sound. Oh, can we hear? We're checking on our phones. Can I hear myself? Oh, it's working. Okay, great. Yeah. And like people just popped in and asked us questions.
Yeah.
Like out of nowhere. I'm like, this is wild. I can't believe this is working. Yeah. But I do think it speaks to the bigger issue. And this is the last thing I'll say about it. I don't want to belabor this or wax poetic about ourselves forever. But that always has felt to me endemic of that. There's a lot of people who are in a position where they feel lost and, perhaps scared or apprehensive about the work in front of them and the research in front of them. And for one reason or another, perhaps they don't feel comfortable asking their advisor, or their advisors are busy. Maybe they have 1 million graduate students or whatever, but people are looking for answers. Mm-hmm. And, we work at an electrochemistry company, and our job is to sell equipment, but also it's to help the community. I'm interested in the next generation of scientists being as good as they can be, because I care about the future of my species and, and the academics and whatever. Like, there's some truthfully altruistic. We're trying to be helpful, and we
yes,
care.
yes,
We do.
yeah,
We
no,
genuinely do.
absolutely. I think Energy has one last question because I do remember there was actually a technical question before. But
Yeah,
this
sorry, I didn't mean
it just
to
makes
skip
more
it.
sense to like just answer his
Finish the-
questions.
yeah,
Just
yeah,
finish
exactly.
them. He asked for any recommendations to people wanting to start off in a similar path with podcasts or content. I mean, my opinion, because I kind of spearheaded a little bit of these efforts.
Yeah.
But really, what seemed to work, there are kind of two things to keep in mind. There's a lot of content that has to do with educational content that is designed to educate people, and then there's content designed for kind of for humor, for entertainment, sort of say. And I've always found that answering people's questions, what people need in general, and what their curiosity is probably the best thing to do. Is like, like we sell equipment, right? We only sell equipment because people need equipment. There's no like, if someone doesn't need something, they're not going to buy it. That's just how it works, or they have really big regret. Actually, Chris made a good point, which is one big key is to make sure you have really good. Yeah.
That was the
Audio
only thing I was
quality
going
is
to add,
huge.
because you've spearheaded most of this, like you said.
Yeah.
My only additional advice is get good equipment.
Yeah.
If you really want to start this kind of stuff, invest in some good. I have no problem. We're not paid by any of these people, but Focusrite, FOCUS, Focus RITE.
Mhm.
It's a company that makes audio interface devices. I've used them for recording music for myself, and we purchased one from our company for what you're listening to us now. So the microphones are plugged into this like thing that's underneath the table. It's down there.
Yeah.
And we purchased these microphones. I forget what's the company for these. This is Focus. All Focusrite stuff.
They're all Focus.
And so these are semi-professional microphones, and this is a filter that, so when I go, you don't hear, hopefully. As I just
until
I
you
spit
actually
into until I actually spit into it. It's supposed to cut out that. So anyway, the point of it, and these fancy arms that we can move around and everything. The point is having good. If you really are interested, in addition to all the stuff Alex said is obviously really, really good, but getting good equipment is really also helpful because, you can just film on your phone, but professionalism matters. It does.
Yeah.
For sure. So I think trying to make sure you have proper equipment. If you can, it's expensive. Of course, we're fortunate enough to work for a company where we can purchase the equipment. We could spend however much to upfront to kind of get the equipment for us. If obviously not everybody is loaded with or fortunate enough to be able to do so. So sometimes you have to work your way up to that.
Yeah.
Well.
Yeah. I think it was like, I don't know, like this equipment, actually, it was like $2,000.
Yeah, about that.
And this
all together,
more,
like everything.
all together.
Mm-hmm.
Like right now, you can see there's a third Focusrite mic here, but there's actually a fourth one, and actually
works, right?
more of these headphones.
Can you hear me through that? Maybe I think it might be muted. I don't know.
I'm not so sure.
I can talk through both.
Yeah, you can talk through both.
Yeah.
But yeah, a lot of this stuff. If you're very serious about it, $2,000 is a drop in the bucket when you consider the outreach and the impact of it.
And monetization.
And monetization.
If you have enough of an audience, you can monetize on YouTube and on other platforms.
You get sponsorships, you can do things like that if you want. So, but you have to work really hard at it, and constantly try to learn and get feedback and improve. Like the first videos that I made for Pine Research were not very good, but like I got better at it, and I continue to get better at it. So also, you have to keep working on it.
Just like anything else, it's practice. I want to go back to Manoj's question. We didn't skip on purpose. This was just a kind of a fun discussion with.
We don't get questions like that.
Yeah, with Energy. I do appreciate that, because obviously we are trying to help with your technical questions, but some of these, I don't know, general or procedural kind of questions are kind of fun too as well.
Yeah.
But Manoj J says how to select the membrane for photoelectrochemical cell H type. What criteria you need? So the first criteria is it alkaline or is it acidic, right? That's the first one. Or is it neither, I suppose. But that's the first main thing, because there's basically a whole host of acidic, right? Or alkaline basic membranes. And the most common one is Nafion, which is an acidic membrane. Nafion is fundamentally a proton shuttle, right? So it's designed. So that's the main thing, right? So if it's a membrane designed for acid, it's going to be obviously stable in acidic solutions. It won't just dissolve when it's in contact with sulfuric or nitric or hydrochloric acid. So that's the first thing, because the stability matters, of course. And then it's it's what kind of ion it helps, because there's usually, you have a separator, they want it to be semi-permeable, and so some membranes like Nafion are designed to allow the transport of positively charged, basically Nafion, the microstructure, to the best of my memory, is that it has ligands with a negative charge on it, and that attracts positive charges to shuttle through. So, opposites attract, and it basically works in some manner that way. Right. And so alkaline membranes are the opposite, where they probably have a positive ligand of some sort that helps funnel negatively charged, whether it's hydroxide or carbonate or whatever it is. But otherwise, there are more generally, people use things like in batteries, they use polypropylene, polyethylene, various polymers like that in a very thin sheet can be used as a membrane. But again, it's like the criteria that you want to pick: acid base, right? Whether it's the stability in your electrolyte on either side of the membrane, and then and Chris had some good suggestions as well. For example, ion selective, what kind of diffusion rate limit, how much current. So I guess most generally, it's the things I just said. It's the stability, whether it's acid or base, right? Those are sort of wrapped together. And then the thickness of the membrane having a lot to do with the rate at which it will transport. If you want to limit the mixing as much as possible, you might use a thicker membrane. It'll take a while for stuff to get through. It might also make it slower, and maybe limit the amount of current you can get out of it or something if it's so slow. But so those are, I don't know. That's about what I would sum up. I mean, do you have anything to add? I don't know, something like that.
Not really. It just I just think about just general membranes for a photoelectrochemical type of experiment. You're shining light on something, you're going to generate some species. There's going to be another species generated on the counter electrodes to complete the circuit. And you just want to make sure that things from both sides don't mix with each other. So as long as the membrane can do that in some capacity, that was because I don't know anything about the electrolyte specifically, or what is the electrochemical test system specifically. You could just have water for all I know.
Yeah.
I have no clue.
Yeah, exactly.
But those are the criteria I think about. But yeah.
What kind of music do I play? I play a lot of stuff so far, actually. I'm not like a recording artist. I'm an electrochemist.
Yeah.
but I do. Yeah, I've played music for most of my adult life. I play guitar, trumpet. I've played drums before. I've written music, and I had a friend's wedding actually somewhat recently, and I recorded using some programs online, like background, so I could play over it and stuff. So just a little bit of an aside there, I guess. But anyway, that was why I mentioned the focus, right? Because I've used it before for my own kind of tinkering and music stuff. Yeah.
Okay.
Yeah. Hopefully the audio isn't painful and people aren't leaving. I know at times there's troubleshooting. The audio popped in and out or something. Can't always control all that kind of stuff, but I think it's been pretty good for the most part. Most of the time, I don't hear anybody saying I can't hear you or anything. So most of the time, I think our audio is behaving itself. Yeah, which is good.
So. Definitely agree.
Yeah, I don't see any questions on Twitter. I'm just checking too.
Yeah,
a lot of people have liked it and followed and shared. So that's very, very nice. I appreciate
retweeted.
That. Yeah,
which is good. Thank you.
Re-X'd. Retweeted.
Yeah,
I don't know. Yeah.
Well, that's it. I mean, if you want, we can stop. We can stop the podcast. It's been almost. It's been almost
2 hours.
2 hours.
Yeah, this is about our ending point, give or
Yeah.
take. So yeah, I guess we can wrap it up here unless there are any other quick questions in the next like 7 seconds. And by the time I've said that, when it gets to you, it's already over because there's a delay. So I've already just told it's over. Sorry. No, I'm just kidding. Yeah. Yeah,
All
we're
right.
good.
Yeah, I think we're good.
Okay.
I think we'll have another one next week.
Yeah, I think
again,
at least for the next
few weeks.
for me, I will not. The next 2 weeks is the 8th and the 15th.
But then the
The
22nd,
22nd and the
probably
29th, I am out of town.
Yeah. I
So
think that might be me too.
Yeah, so probably we'll do 2 more for this year, and then we will be done until the new year.
Yeah,
Probably. Yeah. So that will be our schedule for those who are interested.
Yeah.
And anyway, you'll see because we usually by Mondays or so put up the next event on our YouTube channel.
Yeah.
In advance.
And that reminds me, if you're watching, should have said this at the very beginning, but I
Yes.
forgot. Like, we will have the timestamps in the description.
Yes.
I don't think I have to say that. I'll just put the timestamps and people
That's
will
like
find it.
that's just like YouTube's,
Yeah,
like
yeah,
timestamps are in the description below. Don't forget to like, comment, and subscribe.
That's right.
That's
right.
like every video
Every
for
video.
everyone or whatever.
Yeah, absolutely.
It's just it's YouTube's. Right?
Yeah,
the
yeah.
things you have to say.
Yeah. So Energy
smash
Eve,
that like button. Or whatever. Right.
So Energy Eve, just say that in your videos
Yeah.
because like people will do it. Like you think it's weird, and it's like it's like I feel weird saying it. It's like some people will do it. Like and that's all you need. Like you just need to like.
In fact,
like,
you don't even
they
need to
need
make
a
a video
reminder.
about anything. You could just make a video called like, comment, and subscribe.
Yeah.
Share our videos. Smash that like button.
Yeah.
Just do that. Oh, just say that for like 45 minutes in a row, and that's your video. And then you'll make $1 million. That's how it works.
God.
That's terrible advice.
Yeah,
Just
yeah,
terrible
that's-
advice.
Yeah.
Yeah.
All right. Well,
Well,
very
it's been
good.
fun, everybody.
Mhm.
So, yeah, thank you all very much. We do appreciate you sincerely. Thank you for the questions. Hopefully, we were able to answer some of them with a relative amount of competence. And we will see you all next week.
All right.
Take care, everybody.
Bye.